I'm going to be talking about building and using knowledge graphs today. I'm at the Information Science Institute at the University of Southern California. All right, so first, what is a knowledge graph? So the basic idea is to be able to take all of this information out there that might be in different formats. So it might be on web pages and databases and files, and turn it into something that's, goes from something that's sort of raw, messy, and disconnected into something that's clean, organized, and linked together. Right, so that you have some nice organization of the information that then it's easy to query, easy to analyze and visualize. And there's lots of different applications of this, and I'll talk a little bit more about applications towards the end of my talk. First, let me talk about some of the underlying technologies behind creating a knowledge graph. So here are the various steps that are typically employed to create a knowledge graph. I mean, you have to harvest the data from somewhere, extract the information from those different sources. Typically, that involves doing some organization and cleaning of that information. Then you need to do some kind of alignment to the data. So we do that by mapping the data to some shared domain ontology. Finally, there's usually some entity linking, which is taking the entities from the different data sources and linking them together. Finally, you need to create the actual knowledge graph itself into some format, and that really may depend on the application. And finally, the applications on top of it for querying and visualization. And I'm really today just going to talk about steps 2 and 3 in here, and some specific work that we've been doing in steps 2 and 3 to sort of make the user's life easier to actually create these knowledge graphs. So let me first start with some work we've been doing on what's called semantic error detection. And the idea here is that you have information in tables, and oftentimes there may be errors in the tables. And there could be both syntactic and semantic errors. And we've done work on both of these types of errors, but I'm going to today just focus on our work on semantic error detection. And this is with one of my students, Min Pham, who's working on this for his PhD thesis. All right, so what's a semantic error in a table? Let me give you an example here. So this is a table from Wikipedia, and this is actually a real example. I didn't make this one up. So this is a table that shows the different soccer clubs and their location and the stadium that they play in. And it turns out that one of these is actually incorrect. So this one here in the middle, you can see in red. If you look at the text in Wikipedia, what you discover is that it's actually not aligned with what the table says. So this is actually a semantic error because the syntax is just fine, but the actual content is incorrect. And so one of our goals is to be able to detect these kind of errors automatically. A second example, also from Wikipedia, comes from a table about different shows and when they were actually launched. Okay, and this shows that this particular show, Phone Shop, was first broadcast on a particular date. But in fact, the date in the table is October 7th. The date in the text is November 13th, and the one in the text is actually the correct date. So again, another semantic error. So those are actually real-world examples, some tables that had errors in them. So let's take a look at the first example I just showed you. So what are the challenges then in terms of identifying that this is a semantic error? The first one is we need to be able to locate evidence of this somewhere in some text document, right, that there's a potential problem. And the second challenge then is how to actually use that evidence to verify the information. So we don't know where the errors are going to be. So in fact, you have to actually look for supporting or conflicting data for each one of these pieces of information, and then use that to somehow determine to either support or indicate that there's a conflict. Okay, so what we've been doing then is developing a natural language method to essentially do this automatically. So let me show you another example table. So here's a table of presidents of the United States. So this table shows the year they were president, the name of the president, the first lady, which is, and then the vice president at that time. And so in this table here, there's sort of two pieces that we have to do. So we start in the upper left-hand corner, and we can see that, all right, so if we start with that table there about the presidents, then the first thing we have to do is actually search the text corpus, right? So essentially look at some corpus of documents to see if we can find evidence that either support or provide conflicting information with the information in the table. And the corpus that we're using for our work here is Wikipedia, since it's a fairly rich source of text information and is fairly authoritative, since people have the ability to sort of review the text and make corrections and so on. Then if we take the arrow down to the table below, then there's another thing we have to do, which is essentially look at the overall context of the table. So we can sort of take that information that we're interested in. So let's say we want to look at the relationship between George Washington and the year that he was president. We also look at sort of the attribute names corresponding to that. And then we can do this table linearization, which is essentially turn that tabular information into something that we can then organize around, a set of uh, uh, labeled information, right? So you can sort of see that we have a year, and we have, the corresponding year, and we have the president and the name of the president. And so that essentially forms the hypothesis. And then what we can do is a natural language inference step where we essentially compare our hypothesis about this fact being true, that whether or not George Washington is president in these years, against the evidence from the text documents. And then either find support for that information or decide that there's a conflict. Okay. So here's their overall approach then. So along the top line here, we start with the top line basically involves training the machine learning model that we use to actually determine whether or not there's a conflict or not. And so to do this, we need some training data. And it turns out that there's a nice data set out there called Totto. This data set has information that essentially is going from table information to natural language information, right? So it takes each row of a table and creates a data set that has the corresponding English sentence that would correspond to the information in that table. And so we can use all that existing data to essentially train the model. So this NLI model is the model that gets trained. Then in the middle, on the left side, we have the table itself, right? And so we can take that table and take the information in the table and query Wikipedia to essentially search that and provide some set of documents, do some kind of sentence filtering to provide the relevant sentences from those documents. And finally, we can then compare those sentences that we get from Wikipedia against the table itself. So the set of cells in the table that are serve as input here, those go to the NLI model, and the NLI model compares these things. And then the result is that for each cell in the table, either it's entailed by the information that's in the text or it's contradicted. Okay, so that's the basic approach. And now what I'm going to do is I'm going to really just walk through each step that's sort of shown here in this diagram and explain in a little more detail how they work. Okay, so the first one is this sort of document retrieval, right? So we want to retrieve the set of documents that correspond to the set of information. So you can think of this little red square box as a subtable here. Then we're going to do a hybrid document search, whereas basically we're going to just use a couple of different search methods. One is document similarity, which is essentially what search engines do. So it uses what's sometimes called, TF-IDF to essentially find all the documents that are similar. And then there's some other work on what's called dense passage retrieval, which is similar, but just uses a slightly different method. And, it's another way of actually finding documents that might be about this fact we're looking for, right? The name of the president and the corresponding year. And so the output of that then is a set of documents in the bottom right-hand corner. And then finally, we use something that I'll talk a little bit more in a minute about finding the sentences within that document. Okay, so once we've run that step, right, we essentially find a set of relevant documents. So in this case, it's going to find documents like these shown here, one about George Washington, another one maybe about President of the United States, maybe another one about his wife, Martha Washington. Essentially, we're going to get all these documents that have something about this relationship between George Washington and the year he was president. It probably means that both of those terms show up somewhere in the document. Okay, then the next step is the sentence filtering. So I have a set of documents. Now the question is, how do I then turn that into a set of sentences that I can then query, or I can then compare? So the way this works is that we basically take the document, break it down into the full set of sentences there. That's easy because we have the grammar of the document that we can use. And then we're going to basically run a token-based cosine similarity, which is essentially looking at the set of words in each of these documents and building a vector out of those and comparing for each sentence how close it is to the corresponding words that are actually in the table that we're trying to verify. And so we're going to basically give a score for every single sentence and then essentially keep only the sentences that have a high similarity. So that's how we generate the sentences. And so the result might be in this first document for George Washington, we find that this sentence here, shown in red, is the one that actually has the information that we're looking for, right? That talks about George Washington and the years that he's president. Okay. Okay, so now let's talk about how we actually create this machine learning model, right? So as I said, we're using this existing data set called Totto. And this is an open domain English table to text data set. So it has something like 120,000 training examples in it. That means that these are actually examples that have already been vetted. So we know that there's a good mapping between the information in the table and the actual sentence that corresponds to it. And we're looking at using this information to actually train the machine learning model, right? So in some sense, this provides the set of positive examples that we're going to use for the machine learning. And most of you may be familiar with the fact that in machine learning, we need both positive and negative examples, right? So if this Totto data set provides us positive examples, then we have this challenge. Well, how do we actually get negative examples that we can also use to feed into our machine learning model, right? And so essentially what we do is we use 3 different methods here to generate negative examples. The first one is on the left side here, we can basically replace values in the table with incorrect information. So we can essentially switch information around. So we can take the second row, the name of the president there, and stick it into the first row. So you can see here now we say, okay, this would say that John Adams was president from 1789 to 1797. So that would be one way we can generate negative examples. Then over on the right, we can also do it on the text side, right? Because each example has some table information and then a corresponding sentence. And so instead of modifying the table, we could also modify the sentences. So there's several ways we can modify the sentences. One is that we could take the entities in the sentences, like George Washington, and then again, replace the named sentence with an incorrect name. So we can replace George Washington with Thomas Jefferson. And now this says Thomas Jefferson served as the president of the United States from these years. And again, another negative example. And then finally, we can take the sentence, the correct sentence, and replace it with a completely incorrect sentence, right? So just take a different sentence in the same document. So now we can take the sentence that talks about Washington leading the Patriot forces to victory, and make that the sentence corresponds to the table. And again, that would also be wrong. So you can see there's multiple ways we can create these negative examples. And what we do is we're going to create, just like we have the set of positive examples, we'll also create a set of negative examples that we'll use to train the model. So given all that, right, so we basically now have the full set of the Totto data set augmented with all the negative examples. Then we can do the model training step. So in that step, we essentially are taking some existing pre-trained embedding, right? So these are basically large models that have already been learned that that do this mapping between tables and text. And we essentially add our additional data, the positive and negative examples for what we're working on here, to essentially fine-tune this model. This allows you to sort of take an existing model that already required a lot of CPU time to build, and then really just tune it for a particular type of data that we're looking at here. And that gives us a little bit better model. So that model then feeds back into that overall diagram, and we can then run that. So how does this work? So this is sort of work in progress. So I have some preliminary results here. And when we looked at this, the data set we're using just to test it is the Totto data set. So we're really testing on the training set. So it's not a full evaluation yet. But on the training set for the Totto development set, we do quite well here. So we have 3 scores here, the precision, recall, and F1 score. So the precision gives you, well, the recall gives you for each of the mappings, how many of the correct mappings do you actually find. Precision is sort of a measure of noise. So how many sort of incorrect ones do you actually provide? And then an F1 score is sort of the combination of those 2 measures. And so overall, this looks quite promising, and we'll have some evaluation out later this year with a full evaluation of this. So now I want to turn to, so that sort of completes my description of sort of work we've been doing on identifying semantic errors in tables. And now I want to talk about the second step, which I mentioned in the outline, which is how do we basically infer the description of the semantic model of that data. And that's important because if we pull data from multiple sources, in order to combine those sources together, we need to see how the information across the different sources is related. So this is a really important problem, and one that is often quite labor intensive for the user. And so what we're trying to do is come up with methods where we can completely automate this, right? That the user doesn't have to do anything here. So this is a fully unsupervised method. Let me tell you a little bit about what we're trying to do here. So the source modeling problem in general starts with this table at the bottom. So this is a table, again, from Wikipedia. And it has, and these are the third presidents of the National Council in Austria. The third president sounds weird, but essentially in Austria, in addition to vice presidents, they have someone that's sort of the vice president, sort of, so they call them the third president. So they have a first president, second president, third president. And this table contains for each one of these third presidents the year that they entered office, the year they left office, and the party they belonged to. And then the kind of model we're trying to build here is really a description of this content, right? And so this is what's shown right above the table. So you see here that essentially this person is, a position human. I mean, they're an entity that's a human. They have a position, which is we're using the Wikidata ontology here. And in Wikidata ontology, everything has both a name and a number. So there's a position they held, and in this case, that's a P39. And you'll see we use these abbreviations later. So it's useful to sort of remember these. And then we have each person here has a political party, which is a P102. And you can see that the way this is organized is that you essentially have information about these statements, right? So instead of just saying that this position held as third president, we say, well, this position held is this statement, which includes a property, P39, which is the third president, and includes a start time and an end time, right? So this is just a nice compact way to be able to express sort of complicated statements, right? So statements that have both they maybe have some property like third president, and that they hold over some period of time, with a start and end time. Okay, and so what we're trying to do here then is to be able to build this model of this table automatically. So we don't want the user to have to provide any information. And how is that possible? Well, the basic idea is to essentially use the information that's sort of already embedded in the knowledge graphs. So, Wikipedia is one example of a knowledge graph. Another example of knowledge graph is another one called Wikidata. And Wikidata also has very similar information. It has detailed information about all these people. And so the idea is to actually exploit that information that's already there. So note here that we can actually take one of these entities in the Wikipedia table, follow this blue link, and we'll actually get to the corresponding data in Wikidata about this person, right? So Eva here has a Wikidata entry, and then you can look down at that Wikidata entry and you see that, okay, she was the third president of the National Council, and here are the years before the start time and end time. And so even though these are two different data sources, we can exploit the relationship between the two to basically build this model. And I'll talk a little bit at the very end about, well, what would we do if we have a table that didn't already have some of these blue links? I'll get back to that. But let me talk about first the case where we have these Wikipedia tables that actually already have these links to Wikidata. We can exploit that to basically build a model of this table from the Wikidata ontology. All right, so that's the key idea here that we're trying to exploit. So let me talk about a little bit more about how we do it. Oh, and notice these links here, right? So notice that for Eva, the corresponding start time and end time also show up in Wikidata. Even the party that she's in also shows up. There's some minor differences here that we have to actually deal with. Okay, so the basic approach then to do this is essentially to start with the table. So on the left, we have really the three pieces of information we're using to essentially build this model of the data. The first is the table here showed in the middle. Above that, we have Wikidata itself. So there's this table itself will have links into Wikidata. And so then we have the whole Wikidata knowledge graph that we can use. And then we have contextual values. So these are things like the name of the page or the name of the table. So it's other information that's sort of around the table on the Wikipedia page. And that information is often important because it provides sort of the context for this table. Because if you just looked at this table, you wouldn't know that this is a table about third presidents. But the title right above the table says third presidents. So we use that contextual information. So then there's two steps, right? So we're we're going to build what's called a candidate graph. So this is like, okay, these are the possible sort of relationships in this table that might hold. And then finally, we'll take this candidate graph and distill it down into what we think is the final sort of semantic description of the table. So let me start talking about how we build the candidate graph. All right. So what I've done here is basically I've taken this table. So the table is in the upper right-hand corner here. And I've essentially just created a graph where I take each cell of this table and it has a corresponding node. And I've abbreviated things here. So for example, I don't write out Thomas Prinzhorn because it's too long for my slide. So this node Thomas here corresponds to the first cell in this table. And then 2002 corresponds to the second cell, 2006 corresponds to the third cell, FBO third cell, and so on. And so you see that I have 3 rows in my graph, 4 columns, and that just corresponds exactly to the table. And at the bottom, I have some contextual information. So I mentioned the third president is the title on this table, and so that's one piece of context we can use. Okay, so what do we do with this graph? So the idea now is to basically look at some of the relationships and see if we can infer what the relationships are in this graph by exploiting the information that's actually in Wikidata. So we're going to add these discovered links. And then at the bottom, notice I have I'm just using the P39, P580, P582 in the definition there. And so first thing we're going to do is we're going to say, okay, we'll look up Thomas. And we find there's a link to Wikidata. And so we see that he's in Wikidata with this corresponding information about him. So he's a member of political party FBO. He has a position held, which is the second president of the National Council. He has a start and end time. And so we essentially take that information and we're going to essentially note the links in this graph we've created, so that there's a link from Thomas to FBO, which is the P102 link, which is the member of the political party. And we can do that for the other information. So we can do it with respect to the years. We have on years, we'll have to do some kind of fuzzy matching here to recognize that they're not the exact same string. This is sort of a 2002 is part of 20 December 2002. But we can basically make this same kind of inference that he was second president. And notice this example, which is that Thomas Prinzhorn was both a second president and a third president, just in different years. And so one possible relationship that it finds then is that Thomas Prinzhorn is the second president, even though we know that the table is actually talking about third presidents. I wanted to show an example that that's ambiguous. So there's several different possible things that we could posit as a model of this table, and one of them is that it's about second presidents. So these are these are the statements here. So you can see that we have this Wikidata statement that gets created, and that one of the entity in this case that it's positing is that he's second president. Okay, then we can go to the rest of the graph that we have and see if we can fill that out as well. So we can see that on this one, we'll take the Wikidata information and posit that the other two people, Eva and Martin, were actual third presidents here, right? And the information, of course, with this. And now we can sort of start to try to consolidate the information. So we can do this sort of graph summarization step, where we sort of say, well, Thomas Prinzhorn, right, has this P102 relationship to FPO, and the other two have this P102 relationship to these other two parties. And so we can actually merge all this information together and basically say, okay, we can sort of group the people together and say, okay, there's one overall relationship that name relates to party in this table as the P102 relationship, right? Which is they are the member of this political party. And we can do that for the other relationships here as well. So we can take the information here that the Eva and Martin are both linked to the third president. And again, we can sort of consolidate that information and sort of here show this relationship. Likewise, that Thomas related this second president. But notice that because the second president, basically only one of the years gets covered, right? So it only covers the 2002 and doesn't explain the 2006 year. So it's not really as good an explanation. Whereas because, he became he became second president after he was third president. So he would show up as both. And so here, and you can see that the other two entities here cover both the entered office and left office. we get the final candidate graph here, which shows that, okay, these people, they may be either second presidents or third presidents, right? It covers, some of them cover entered office, some of them covered entered and left office. They all cover this party. And so we can essentially use this to essentially create this final candidate graph, right? So this is a graph that sort of has all the possible relationships in it. Doesn't have the final model, because you can see we have several sort of conflicting information, right? We don't really know, is this about third presidents or second presidents? And so and we also have some ambiguity in terms of what these entities are, right? So for example, is this node here, the labeled party, is it correspond to a political party, or does it correspond to an organization? Because both of those are possible things in the wiki data ontology. So after we've built this candidate graph, now we need to select the most appropriate relationships and types. And that really corresponds to the final step here, where we build this semantic description. And given the time today, I don't really have time to cover exactly how we do that, but we essentially do an inference step here, where in some sense you can look at sort of, well, how frequent were these different things, right? So in this case, it was more common that these people were the third president than the second president. So that seems to be a better explanation. Plus, in this case, the explanation of the third president covered both the entered office and left office, whereas the second president only covered one of those. And so it turns out that the third president then is sort of a better explanation of this particular table. And so that would be the final inferred semantic model, the one I showed you at the beginning, which would actually cover this data. So in terms of evaluation of this work, so this work was published at a recent conference, and we compared it with several other systems. So there's another system called Mantis Table, another one called BBW. Grams is the name of our system here. And then we compared it on two different types of data. So one was 250 Wikipedia tables that were selected at random. And the second one is a set of synthetic tables that someone else created called SemTab 2020. And then we compared all the systems, and again, just as before, we compared them using precision recall and F1. And there's two different comparisons. One is, did we figure out the correct label on the column, right? What's the type of the information that's actually in the column? And the second thing for the CTA here is, do we find the right set of relationships between them? And the black in each of these rows indicates the best performance. And so you can see that either grams or a variant on grams, gram B, did well on almost everything. The only exception is that BBW gets similar performance on one of the tasks on the synthetic tables, but it gets outperformed on the CTA task. And then one of the other ones, Mantis Table, has higher precision on the CTA task than Grams got. But if you look at its recall is very low, right? So it's easy to get high precision if you have very low recall. So 0.394 is 39%, whereas Grams has 81%. So overall, Grams has the best performance on these tasks. Okay, so I mentioned that one of the things I assumed in the work I just described was that each of these entities was in the original table was already linked into Wikidata, right? So we exploited those links to basically be able to infer this model without any user labeling, right? So no user input, it just would produce the final model. So what could we do with a table that didn't have these links? So let's imagine that we have the table on the left in this figure where there's no links. And so we're working on that now. And basically what we're doing is an entity linking step where essentially we take each entity in the table and first link it into Wikidata. And then once we have those links, then we can run this sort of Grams algorithm to automatically generate the model. And that is work in progress, and hopefully we'll have some results on that soon. Okay, so let me just quickly, I'm running out of time, so let me just quickly mention a few applications we've built in terms of using knowledge graphs. One is for fighting human trafficking. So here we've collected a large amount of web data, turned that into a knowledge graph, by essentially extracting the information out of all these different online websites, and then built a very large knowledge graph out of that. And that was a very successful knowledge graph we built. It was actually deployed to something like 400 law enforcement agencies to actually use in their combating human trafficking. And we had reports from both the district attorney of both San Francisco and New York City that this knowledge graph was extremely useful for them in terms of actually doing the prosecutions, right? So they could actually get the data they needed to build the case to prosecute the traffickers. A second example of this is finding illegal arms sales. This is work we did with ATF, called Tobacco and Firearms in the United States, where they were interested in finding people that were illegal selling arms across state lines. And one of the ways people would do this is they would buy guns on one website, and they would actually sell them on a different website, so that someone would notice that you're buying and selling across state lines. And so here we were looked at methods for automatically, basically being able to take a page or the entire website, for a given arms site, and essentially turn that into a knowledge graph, and then be able to link the information across the different websites. A third example is some recent work we did on identifying threats in space. So here we were basically collecting open source information about satellites, and we were looking for detailed information that is in the public domain that talked about the satellites. And then we looked at using machine learning techniques to essentially characterize the different satellites. So, if someone put up a satellite and they say, okay, this is a weather satellite, we could essentially look at all the other weather satellites and build a model of what a weather satellite looks like, and then compare that to a given satellite and sort of say, yeah, this satellite is claiming to be one thing, but it actually appears to be something else because it doesn't appear to actually act like the other weather satellites. And so that's another example of a knowledge graph that we built. So, okay, let me just wrap up then. So I've talked about two different sort of technologies for essentially helping with the automation of building knowledge graphs. The first one is this on the left here, this semantic validation of a table. So, taking this table of information and essentially marking it up so that, we either say, okay, we found support for this information, there was no information we could find to verify it, or there was a potential conflict. And in a potential conflict case, ultimately you'd probably want to bring in the user to sort of say, okay, is this really a conflict, where they could actually see both the table information and the text information and sort of determine whether or not there really was a conflict there. And the second thing was this automatic table modeling, right, where I basically take a table of information, build the model automatically. And the advantage of this, of course, is now I can take multiple tables of information, automatically build the models for each one of them, and now I understand what the relationship is between those tables, so I can combine that information into a larger knowledge graph. And this is an important problem. Like in the case of the ARMS sites, I'm bringing in tables from hundreds of different websites. Each one of them has their own sort of model of the data, but by building this model automatically across them, I can now combine the information and figure out what the conflicts are, figure out where there's an entity that might be bought on one site, sold on another